Greetings, the Astro 30 here again on this discrete amplifier. Well, it's turned into a project now. Basically, I'm going to start routing out the PCB for this because it's nearly ready. When I say nearly, if you remember from the last part, which was part 2, I noticed there was at least a 1 odd volt either in the plus or minus DC on the output. Now, there could be several reasons for that. Number one being the current layout of the circuit. Everything is everywhere. As you can see, there's wires running here, wires running there, and here, there, everywhere. Here a wire, there a wire. Old MacDonald had a farm. Or it could be a simple circuit design issue. First thing I'm going to try is this feedback gain network here. For some reason the original design uses like a 100k resistor as the feedback resistor, so it's getting very little negative feedback there, and a 4k7 gain resistor. So what I might change these two resistors to is 22k and 1k respectively. They'll give us a gain of still 23, and see if that will lower the total DC offset. I don't think it will. And failing that, I'll move over to this section here on the input stage. Now, if you remember, this is the old schematic. Here we've got a current source for the input stage and the output stage here. Now, I haven't changed anything down here. Now, I can add a current mirror as described in the last video. But mainly DC offset of an amplifier is controlled by this first input transistor. And I have tried putting a variable resistor in place at this 4K7 and varying it. And when I put it to 0, I did hear something catch on fire. It went pfft, I don't know what it was. Anyhow, that didn't seem to affect the overall DC offset on the output. So that's what led me to believe that it's probably the wiring itself. The first thing I'm going to change, as I said, I'm going to try changing this 100k and this 4k7 and see if that lowers our overall DC offset output. Well, there are many reasons why an amplifier can have a perceived DC offset as represented on a multimeter in the DC scale anyway, and one of them is not too thought about that much, which is oscillation. So if I turn the load on with no input connected, all we see is just a bunch of random noise. Nothing really spectacular. The amplifier is not oscillating on any frequency that I can see anyway. So what does this mean? Not much, but that could mean that it's just piss poor layout. So anyway, let me change that gain structure. I'll just turn the DDS on so we can see a signal rather than just noise. And there goes the DDS at 100 millivolt. So I'll change that back to 500 so it's actually doing something. There we go. And our time base is off a little. So put that back to 2 milliseconds so we can see it. Yeah, not bad. Right. It's not exactly stable either. So let's stabilize that. There we go. Now, it looks reasonably okay. But yeah, the signal is a little bit on the noisy side. Just disconnecting the Zobel, reconnect the Zobel. So what I might try first is, as I previously stated, was changing that gain structure a little and just see if that cures the DC offset. Just to confirm, I need to reconnect my output back to the multimeter so we can actually see the DC offset. Okay, multimeter connected across the output, turn the load on. Yes, and we have a minus 1.2 volt thereabouts DC offset. So I'll get the gain structure changed and then we'll have a look. Okay, got that 4K7 changed to 1K and that 100K changed to 22K, and we've now got a gain of 23 which is roughly what it was to start with. So we look at our multimeter, which is dropped back off to about 47 millivolts. We'll turn the load on. And well, interestingly, we've now got, interestingly, we now have 700 millivolt and falling DC offset. That is very interesting, isn't it? So just that one change alone has had an effect. It's still a little bit too high, but it has had an effect on the overall DC offset. So the next thing I might try is I might change these BC 557s to BC 556s respectively for both input transistors there, and then see if these particular choice of transistors are just inherently noisy, which noise would actually be a good reason as to why we're getting a larger DC offset. Yeah, and then I might play with this collector resistor here, just to see if we can drop the DC offset even further. Before I go to the point of adding in a current mirror down here, because that's 2 extra transistors and 2 resistors that doesn't really need to be on the BOM or bill of material. Okay, the 2 input transistors are now changed. Now we'll look at our multimeter again. Load is not on, but it is now. And as I thought, that wouldn't do anything different to the output. So we've still got 600 odd millivolt DC offset, which is still too high. But the circuit's working fine with that choice of transistor. So next thing to try and change is this resistor, this degeneration resistor in the collector of the first transistor, because this resistor will actually control the whole DC offset of the circuit. Although I couldn't get very far with a variable resistor the other day, but we may do today. So I've got a 50k variable resistor here set to around about half its resistance. I'm not sure if clockwise is 0 or the other way is 0. I'm pretty sure it's clockwise is 0 because of the way it's configured. Right, so that's just in place of that fixed 4K7 resistor. So if I turn the load on now, got 700, 600. So if I rotate the pot in the clockwise direction, we can see that that's fully clockwise, that the DC offset's only changing slightly. So if I go in the counterclockwise direction now, we can actually see it's dropping right off. Whoa. Right, yeah, that is more respectable. I don't want to go too far in case I cause something to catch on fire, because using a control like this is not good. I'll try and get it close to 0, but it keeps going to 27. Okay, so we're about 400 to 300 odd millivolt. So what I'll do is I'll measure the resistance of that pot and then take it to the next closest value, and we'll see what the actual DC offset is then. But of course it still could be circuit layout here as well causing the DC offset, but that's the thing I'm going to do next. Okay, so on the ohm scale, I've taken the pot out of circuit. On the ohm scale, if I measure across the pot here, yeah, we've got more like closer to 1k there. So I know it's around about 1k, would probably be a bit better. Okay, so without making this part of the video too long, I've got a 1k in there now. I'm probably thinking it should be more closer to 560 ohm, but I don't have a 560 ohm, I've got a 470. Now the reason I didn't do this in the last video is because simply I ran out of time and I needed to get the thing edited. So, turn the load on. We've got 440 millivolts, so we've shaved off 200, so I reckon maybe a 470 ohm resistor would work probably a little bit even better. Let's try it. Okay, 470 ohm is in. Turn the light on. Would you look at that? That's even better. So, wonder how far we can take this. 220 ohm, maybe. So we look at it on the millivolt scale. We've got 211 millivolts minus, but yeah, it's more respectable DC offset than what was there. Yeah, so let's try a 220. Okay, got a 220 ohm in there now. Yeah, still 200 odd millivolt. I don't think I'm going to get it any lower than that, to be honest. Yeah, I don't think that's going to get any lower. I mean, I could put a current mirror there, but I just don't see the necessity to doing that. I mean, if I touch the wires on closest to the ground there, it's going all over the place. So yeah, most of the rest of the DC offset or noise that's on the output is mostly because of the wiring here. So proper PCB layout would most likely get rid of most of that DC offset down to almost zero. And see, now it's going all over the place, it's not even stable now. Okay, alright, we'll hook back up to the scope, turn the signal on, or I should say the amplifier on. Nothing unusual. I'll turn the DDS on and make sure I've still got a signal. Notice how the DDS is pretty noisy on its output. And yes, I've got an output, albeit now it appears to be a little bit not stable on its signal output. Not sure why that happened now. Nothing I do seems to clear it up. But yeah, okay, it's outputting a signal, and we should still get our maximum output of 25 watt. Albeit that's a bit cleaner. It just can't seem to stabilize itself. It's just the wiring on the board here. I'm touching one of the ground wires and it's making a difference. So we can discount this crap at the bottom here. Excuse me. We're actually getting slightly more, 41 volt than we were before. That's at 450 hertz. I forgot that we're at a different frequency range now. Change that back to 1 kilohertz. 43.2 volt. Now, is that clipping though? No, I've got no signal at all. Yeah, we're getting 42 volt. It's not, that cleaned it up. It's not clipping yet. 4.9, 1.9, 2 volt, 2.1 volt. Change the time base just so we can see the waveform a little bit better. It's starting to clip at the bottom. So yeah, it's about 2 volt peak to peak is our maximum input sensitivity. So yeah, no, it's still working, so fairly good. So we've got a little bit of a better DC offset on the output. So let's look at the changes. So first, that should be a 22k, that should be a 1k, and this resistor off screen down here should be more like a 220 ohm. And that should be sufficient enough changes there to make the amplifier work closer to where it should be in the DC spectrum realm. So with that little bit of experimentation out of the way, it's really time to start doing the task that I've been putting off for quite a while now, is laying out the circuit board for it. That's going to take the most time, so I'm not probably going to have the circuit board manufactured today, but it will be manufactured by hopefully the end of this week coming. But it'll be in the same video as this, so when I cut from this last bit of experimentation, the next shot picking up from there will be onto the circuit board. But I'm pretty well happy now that the thing is operating as it should be, even on breadboard. So on a PCB, if it's laid out correctly, it should operate even better. Yeah, so we'll just go from there. And oh, the other changes I made with these are 556s, but that didn't make any difference to the performance of the circuit. So before I go on to the circuit board, I'll just have a listen to the output with nothing connected. Ugh. That sudden turn on is a little bit of annoyance. Noise-wise, I can't hear much coming out the speaker. Might be a slight hiss there, but not as pronounced as it was. No, that's all well and good. Disconnect the input wire here. Okay, yeah, alright. It's not as noisy as it was, put it that way. So, slight pop-it turn off. But that sudden turn on thump is kind of annoying. And it doesn't always do it all the time, but it does do it most of the time. Yeah, that's that's not a good turn on transient, let me put it that way. So I don't think I can do much about that. So let's move on to laying this circuit out on a PCB, get the thing manufactured up, and see what the final result is. Okay, and a few hours later I have actually got the PCB artwork done. Up the top here, sorry about that, up top here are all my 0-volt rail or ground reference returns to that central point. There's a couple of blemishes there which I have to get rid of because scrape that off slightly, and there's a track here that's not complete, and there's another one down here that needs just a little bit of a touch up. And I'll just touch up the areas that need to be fixed with a little resist pen, just to fill in the gap. Hopefully that's good enough. Everything else looks alright, so that's the first thing you always do when you expose a pattern, is to check your developed board thoroughly. Okay, about an hour and a bit later, I've got my PCB all cut, drilled, etc., protected, just waiting for it to dry a little bit more. I seem to have, I don't know if that's copper or whether that's just a bit of doesn't look conductive, just looks like a hair or something. I need the multimeter. No, it's not conductive. Okay, so it just must be a hair, or the where the spray just bubbled or whatever. The only thing I've got to watch is these traces at the edge of the board here. They're very close to the edge of the board. I just cut the board a little bit too beyond the line there, and just got to make sure that that's not going to come into contact with the heatsink. I've also got to get my parts laid out next to me on the desk. Got a PTC, an RXE 160, which has a trip current of about 2.5 amp or something. That's the poly switch for the output in case it gets shorted to ground. I'm going to use these splay terminal connections that you put into a PCB and you solder, and they are a fairly tight fit, but I like a tight fit, so that's what she said. So yeah, I've got to get the parts organised for that, and here is the overlay diagram. As you can see, it's not overly complicated. It's spaced out reasonably well. I ended up going for the option of mounting the driver transistors to the main heatsink plus the BBE multiplier, and there ended up being 2 link wires on the circuit board. That is unavoidable with single-sided. Plus voltage in here, minus voltage in here, ground there, input there, output right there. Everything's board mounted, and I'm going to build everything up on the circuit board bar this section that goes to the heatsink, because I need to mount it to a heatsink. I do have an idea for that. I'm hoping it works. But what I'm going to do is I'm going to assemble the rest of this circuit board here in time lapse, because, well, a lot of people seem to like that. I don't know why. And I'll get it up to the point where these transistors are about to go on, and then we'll look at what I'm going to do for heat sinking. And for the input terminal, I'm going to use one of these, as I normally do, because they're quite easy to use. So let me just get my parts all sorted out and we'll get started. Right, so there's me circuit board all assembled there. Only took about half an hour, 35 minutes, something like that. You may be saying to yourself, aren't these traces rather thin? Well, they are, but they're only on the low voltage side, well, low current side of the circuit. These thicker traces are the high current side. It should be okay for the amount of power this is going to be putting out and how much current DC wise it draws, which is about 1.5 amps at full power output. So it shouldn't be a massive problem. Now, on my schematic, I've got this 220 microfarad incorrect polarity in the circuit. The positive should not be going to the negative 35 volt rail, it should be going to the 0 volt rail. So that capacitor is backwards in the schematic, but it's correct on the layout. So the next thing to do would be to mount this to a heatsink. Now, there's supposed to be a 150 ohm resistor right where this 100 ohm is. I put 100 for some reason on the circuit, I don't know why. It should work the same, that's part of the constant current source. If I get any weird results on the scope, I'll change it to 150. Just bring the board down a bit, that's about right. Okay, so everything is soldered in. I've just got to be careful not to bump these transistors up against the heatsink. So now we're ready to do the first preliminary test, which is power it up with two 470 ohm resistors, well at least one anyway, across one of these rails so I can do the bias adjustment here. So I'm going to have to pop you on the floor. Okay, got everything set up. I've got a 3 amp fuse on the negative side. Got the fuse removed on the positive side, going across a 470 ohm resistor across the meter in the voltage scale. I'm going to limit the current to around about 500 mA just in case anything's not quite right with the circuit. And I'm going to leave it at the 25, 26 odd volt plus minus that I've got. Turn the load on. No excessive current draw, and we've got 7.2 volt on our output. Well, 7.2 volt as in quiescent current. So if I now remove current limiting so that it's got the full available current going into the power amp, and I now turn this pot, I've got to figure out which way it goes. I think it's just clockwise for it to increase. No, that seems to be decreasing, so it's anti-clockwise. Now I've got to slow down a bit. But using a 25 turn pot actually makes it a lot easier to set this to where it needs to be. So we're about to 11.5 now. That should be for a current flow through the output of 25 mA. Now if I touch my VAS transistor, my VBE multiplier transistor, I can actually see the voltage is dropping off. They're at 11.24 now, 23, etc. going down. Now if that was connected to the heatsink, that would work a lot better, but it's not. Now if I remove my finger and let the transistor start to cool down, we can see that it's starting to climb back up. So it might take a while for that to stabilise, but I can see that the VBE multiplier plus the output stage is functioning correctly. So the next thing to do would be to turn it off, and I'm going to put the other fuse back in, and I'm going to connect the meter now across the output and ground and see what our DC offset is. Okay, the other 3 amp fuse is now in. Turn it on. And look at that. We've got around about 97 millivolts, which is absolutely fine and absolutely perfect. It was hovering around about 400 before. So yes, layout is extremely critical. But 100 millivolt minus in this case on the output, perfectly alright. Okay, so we know that that's going to be okay and safe enough to connect to a load and a speaker, and that was tested unloaded by the way. Next is to hook up an input signal and an oscilloscope and see what the output looks like. Okay, got all that set up now. Just got to make sure that that lead doesn't short on the ground there, or else we're going to have no output signal on the input connector there. So I'll turn the load on, and yep, we've got a nice stable sine wave output. Now I'm still at my 1.8 volt peak to peak in, which is the maximum before clipping, I believe, and we've got a good 40.7 odd volt peak to peak out. We'll do a couple of calculations in a minute. Just going to quickly check my output stage. It's getting warm. What was I doing? Yes, doing the maximum input. So at 1.9, 2 volt, and it's starting to clip. So I want to say around about 1.8 to 1.9 for maximum out. I'll ballpark it at 1.8. It's actually 1.9 now. We're getting 43.2 out, which in actual fact is a lot better than the breadboard version. So we got what? 43.2. 0.2 divided by 2 equals 21.6. Just turn the RS down, multiply that by itself, equals that divided by 8. Holy shit, 58.32 watts, that's peak. And the RMS value of that appears to be 12.6. So 12.6 multiplied by 2, no, multiplied by itself. 158 divided by the load. 19 watt RMS. 20 watt, give or take. That's only running on 26 volts, not running at the full 35 plus 35. Let's have a look at our sweep function. At full power output, and it looks reasonably flat. So it's got a good flat frequency response, so that's not too bad. Still going. And we're actually clipping a bit. That's only because I got the amplitude too high. I want 1.5 will do. Volt. That's a bit easier to see. Yeah, that looks reasonably flat. I'm sorry if this video is going on longer than necessary, but I just wanted to make sure that I'm showing all the information that's relevant to this project, and just proving that my PCB version actually works a little bit better, actually a lot better, than the breadboard version. It proves a point that breadboard is not a good substance for making a power amplifier on, because of all the wiring and the capacitance that's going to be added because of the way the breadboard is. It just adds extra capacitance to the circuit, so it's definitely no good for RF circuits. Let's just get that straight. So if you want a breadboard out an RF circuit, forget it. Use a piece of copper clad, and then, you know, cut out with a knife or something breaks in your tracks where you want, and dead bug solder all the components to the copper clad or etch a board, whatever, and just make sure you've got a good ground plane. And yeah, RF circuits can be built to be tested that way, but not on breadboard. So I'm happy with that. The frequency response is relatively flat, so I should short circuit the output and see if the protection works, but I don't really want to in case it goes bang. So I'm not going to do that. So we're just going to go back to continuous wave and stare at that a while. But what I'm going to do is I'm just going to let this get nice and hot. Those actual 5-watt resistors are quite hot, but of course the thing's not going to be running at full power the whole entire time through its life. But yeah, I'm just going to let that run for a bit, and then we'll do a sound test. Okay, so we're almost about ready for a sound test. I've got the input unloaded. I'm just going to turn the power on. I've got it connected to a speaker. Okay, a little bit of a thump there. Really need a muting relay. Okay, sounds okay to me. So now I'll connect up some input leads to an audio lead to the laptop, and we'll just play some music. Okay, let's get this all important sound test out the way. Let's play this track and see what it sounds like. That seemed alright. Okay, so what next test I want to do is I want to short the output, preferably without the amplifier driving the speaker, like it's not amplifying anything, it's just got no input. So shorting the output leads together, and hopefully it doesn't destroy the output stage. If anything, it will just blow a fuse. So what I'm going to do now, fix that problem. I'm shorting the output. Nothing seems to be happening. It's drawing about 100 mA when I do that. So the output protection with this PTC is actually doing its job. So it's protecting the output stage from being damaged due to accidental short. So let's do that again with the output. Doesn't hurt it. Alright, so that PTC will protect the output. If anything, it just lowers the volume of the output. in this particular case anyway. But generally speaking, the amplifier is stable. It doesn't have any thermal runaway characteristics that I have found. This ground lead to the input socket's not very good, but yeah. It doesn't have thermal runaway characteristics. Everything is remaining cool, even when it was driving the speaker quite loud. So for a project that's taken me about a week and a half, and the actual circuit board, I actually did this all in one day, mind you. This circuit board design, cutting and etching and whatnot, to get it to this stage. Excuse me, all in 1 hour. 1 day. It'd be nice if it was done in an hour. But I got it done in a day. Even though I lied in the beginning of this video and said I wouldn't have it finished today. Well, I persisted. I have it finished. It's now just after 5:30 at night, and I started working on this board layout around about 11 o'clock. So all well and good. So I'm very happy that that's turned out. It's got a reasonably low DC offset of 100 millivolts thereabouts. Anywhere between that and 150 is fine. Any higher than that, and yeah, it's starting to get a little bit iffy. Everything seems to be okay. That's the constant current source for the biasing network, and that transistor is hot, but it's not overly hot that you can't just hold your finger on there. So, and that shouldn't change during operation at all. It should remain a constant heat. Anyway, I'm going to end this video here, and I hope you enjoyed it. I'm the Astro 30, and if you did enjoy this video, please remember to rate, comment and subscribe below. And you can always follow me on Facebook and Twitter. The links are in the description as usual. And anyway, this is the Astro 30 saying thank you for watching, and cheers. Excellent. That's well worth it after a hard day's work.